video, let me consider two numericals on maximum power transfer theorem. What should be the value of R such that maximum power transfer can take place from the rest of the network to R, obtain amount of this power for the circuit shown below. So for this circuit, we are supposed to find the value of R such that the maximum power will be delivered. And the second problem is, for the circuit shown below, determine the impedance ZX such that maximum power is transferred from the source to the load ZX. Here we are supposed to find the value of ZX such that the maximum power will be delivered. Let me consider the first example. Let me consider one numerical on maximum power transfer theorem. What should be the value of R such that maximum power transfer can take place from the rest of the network to R? Obtain the amount of this power for circuit shown below. This is the given circuit. We are supposed to find for what value of R the maximum power will be delivered to R, and we should also find that maximum power. So here we are supposed to apply the maximum power transfer theorem. We know that the maximum power transfer theorem says that maximum power will be delivered to the load when load impedance is equal to network impedance. To find the maximum power transfer to the load, we should bring this circuit to Thevenin's equivalent circuit. So here our first step is to bring this network equivalent to Thevenin's equivalent circuit. So here we are supposed to find the R value. So first remove this R branch from the network which is connected. So here first we are supposed to remove the branch R which is connected between node A and B. Let me redraw the circuit by removing R. So the circuit will looks like this. Now we are supposed to find the voltage between terminal A and B. That voltage is known as Thevenin's voltage, that is, or open circuit voltage, VOC. So let me find VTH. So here we can see that the current 5 amp, entire current will flow through 2 ohm resistor. So I can write voltage across 2 ohm resistor is nothing but voltage at this point, that is VA. Voltage at point A is VA, which is equal to 5 into 2, which is equal to 10 volt. Similarly, here we can see that we'll try to find the voltage at point B. I will call it as VB. So VB will be equal to, let me assume that current through this is I. So VB will be equal to 5 into I. Let me find what is I. So here I can be calculated as I is equal to, apply KVL to this node loop, that is 24 is equal to 10 and 5 are in series, 15I. Therefore I is equal to 24 by 15. So therefore VB is equal to 5 into 24 by 15. Therefore VB is equal to 8 volts. So this is VB, this is VA. So therefore VTH will be equal to VA minus VB. VA minus VB, that is VTH is equal to 10 minus 8, that is VTH is equal to 2 volt, or VTH is also known as open circuit voltage, VOC. Now let me find the Thevenin's equivalent circuit. Now let me find the Thevenin's equivalent resistance, that is the resistance between terminal A and B, keeping all sources set equal to 0. Now to calculate RTH, set all sources to 0. So here current source will be open circuited and the voltage source will be short circuited. Let me draw the circuit. Here we have 2 ohm, this is terminal A, and here we have 5 ohm, this is terminal B, and here we have 10 ohm, and this is short circuited. The circuit is like this. Now we are supposed to find the equivalent resistance between terminal A and B, that is nothing but Thevenin's equivalent circuit. So here we can see that 10 and 5 are in parallel. So I can 10 is parallel with 5, which is equal to 15 divided by 50 divided by 15. So that now the circuit will be reduced to, this is 2, and here we have 50 by 15, that is A, this is B. Therefore RAB is equal to 2 plus 50 by 15, which is equal to 5.33 ohm. So now let me draw the circuit, Thevenin's equivalent circuit. That is, we have VTH, that is 2 volt, and the resistor is 5.33. Now here we have to connect. This was terminal A, this is terminal B. Now here we have to connect the resistor which we have removed at the beginning, which is R. So maximum power transfer says that the maximum power will be delivered to R when this value is equal to this value, that is R supposed to be 5.33, then only the maximum power will be delivered. So let's calculate the maximum power, that is, let current through this is I, therefore 2 is equal to 5.33 plus 5.33 I, therefore I is equal to 2 divided by 5.33 plus 5.33, which is given by 0.1875. Therefore the maximum power will be given by, that is 0.1875 square into 5.33, that is square into 5.33, it gives 0.1874 watts. So this is the required result. Consider the second example. Let this point be A, this point be B node, let this be C node. So to calculate Zx, first we are supposed to remove this Zx from the network. So here we can see that the source is 2 sine 2t, that is 2 sine 2t. It is of the form 2 sine omega t. If we compare with, it is of the form 2 sine omega t. In that case omega will be equal to 2, that is omega is equal to 2 radians per second. So with the help of this omega, we'll calculate inductive reactance XL and capacitive reactance XC. So we know that XL is equal to omega L. So omega is 2 into L. L here is, this is 1 L, 1 by 2 Henry, that is 1 by 2, which is equal to 1 ohm. Similarly XC, we know that 1 upon omega C. So 1 upon omega value is 2 into capacitor value. Here the capacitor value is 1 by 4, that is 1 by 4, which is equal to 4 by 2, which is equal to 2 ohm. Now to find Zx, we have to remove this Zx from the network and we have to short circuit the voltage source. So let me redraw the circuit. Here I have short circuited the voltage source. I will replace the inductance value, that is half Henry, by J1 ohm, inductive reactance J1 ohm, and this will be minus J2 ohm, this will be minus J2 ohm. Now we are supposed to find the equivalent resistance between terminal A and B. So here we can observe that minus J2 and this J2 are in parallel, these two are in parallel. So here these two resistors are in parallel, that is minus J2 is parallel with minus J2. Solving this will get J2 into minus J2 divided by minus J2 minus J2, which gives, so it will be minus minus plus J square into 4 divided by, we have minus 2 J2. So J square value is minus 1. So it is minus 4 divided by minus J2, which is same as minus 2 by J2, which is nothing but minus J1. So let me redraw the circuit, that is equivalent circuit of this. Say this is node A. So to node A, 1 and J1 are connected. That is, we have J1, this is connected to node A. In series with that, 1 ohm is connected, that is 1 ohm. And here we can see that B point and this point and this point are same. So let me connect it to here. So this is point B, that is this point and this point are same, that is this point. Let me call it as D. So this is D. So now to the point C, 1 ohm is connected between A and C. So this is A. Between A and C, there is 1 ohm resistor. Say this is point C. This is 1 ohm. And here we supposed to connect minus J1. That is minus J1 is connected to this point. So now from this circuit we can observe that this is 1 plus J1 and this is 1 minus J1. These two are in parallel. Therefore, we can say Z equivalent is equal to 1 plus J1, that is 1 plus J1 is parallel with 1 minus J1, 1 minus J1. So therefore, Z equivalent is equal to this into this divided by this plus this. That is, it is of form A plus B, A minus B, that is A square minus B square. Let me simplify. 1 minus J1 divided by 1 plus J1 plus 1 minus J1. So it is of form A plus B, A minus B, that is A square minus B square, that is 1 A square minus J1 square divided by, here J1 will get cancelled. So this is equal to J square means minus 1, that is 1 plus 1 divided by 2 is equal to 1. Therefore I can write Z equivalence is equal to, so therefore Z equivalence is equal to 1 plus J0 ohm. Here there is no imaginary term, only there is a real term. So maximum power will be delivered to Zx. So according to maximum power transfer theorem, the maximum power will be delivered to Zx when Zx value is complex conjugate of network impedance. Therefore, complex conjugate of this is 1 minus J0, which is equal to 1 ohm. So this is the Zx value. So if you choose the Zx value as 1 ohm, then maximum power will be delivered. Thank you for watching.